All right, guys. We are going to look at how to theoretically get to work through this problem. So what we got to do on this is we got to think about a system. What are all the things involved? So we're going to go through this one step at a time. So I have a weight force right here on the little guy. So it's little m. I'm going to use a little m for the little guy hanging. And from the situation that we saw is that it's 10 grams hanging and it's 300 grams sitting up top. Okay. So that is the weight force. There is also, let's get it on here, a tension, right? So there's a tension right here pulling that large mass forward. There's also a tension upwards on this guy. Okay, these tensions are what we call third law force pairs. They cancel out. All right, there's some more forces. We also have a weight force on this large mass. Okay, and there's one last force. That large mass has a normal force. The air is pushing up on that cart. Look at what happens though. If I think about that upwards normal and that downwards weight, they're going to be equal. They're going to cancel each other out. What in this problem is not canceled out? The normal and the weight are canceled. The two tensions are opposing in opposite directions. They cancel. The only thing in my entire system that does not get canceled out is the hanging mass. So we're going to use that idea to attack this. So I have one equation that deals with acceleration, and we're going to use it all the time. But what we're going to do in this one is different. We're not going to look at an individual object. We're going to look at the system. So the system is both of these objects together. So in the system, what is driving the objects is just the small masses mg. The big masses mg is not accelerating it. If that string wasn't there, the red cart wouldn't start moving on its own. Okay. On the right side, what is my mass that's involved? How much mass is being accelerated? So let's watch. So the little one is being accelerated, right? And if I think about that video, that red cart is also being accelerated. So both of the masses are being accelerated. So the acceleration is the mg of the hanging mass divided by the mass of the little guy plus the mass of the big guy. What we're going to do is we're going to plug in our values now. So we have 10 grams, 0.010. So kilograms. I'm going to write kilograms just to make sure it's clear what these values are. So to turn to grams, kilograms, if I divide by 1,000. G, I'm going to use 9.81 to get it as accurate as possible. Okay, because we're using very accurate masses here. So let's see what we get. And then below, I have the small mass plus the big mass, 300 grams, put it into kilograms. These are all kilograms. That equals my acceleration. If I plug that into my handy calculator, I get 0.317 meters per second squared. Is that anywhere close to 9.8? No. Did we use 9.8 to solve it? Yes, but here's the big thing about this, is that because that mass is up top, it does not accelerate at 9.81 meters per second squared. Okay, so what we're going to do now is go back to that Google form. And in that Google form, what you're going to do is, first up, you're going to write in the answer of the video you just watched here. But I'm going to give you another problem, and if you can't do it, I'll have a little help to help you. So, all right, so let's keep going.